joint work with Andrea Bastianin and Luca Rossini, was titled, as you just mentioned, is Quantifying Demand Shocks in the Grid and Digital Transition. And specifically, we will quantify these shocks in the context of structural VR models for critical raw materials markets. And this is a bit the outline of the talk we're going to be having. It's pretty standard. We will have an introduction, see the data and methods, the results, and we will conclude with an extension exercise. Okay, but what do we do? Well, what we do in a couple of sentences is simply first estimating demand indicator for these critical raw materials, and then exploit them in structural VF model. And specifically, the first motivation to do this were behind this paper was that we wanted to improve the data availability of critical raw materials because for those of you who don't know, studying critical raw materials is very difficult, and that is because we don't have much data about them, and the few that we have are short or are longer at high frequencies, and so this make it difficult to study them precisely. And so, as I was saying, our first aim is to build a new monthly proxy for derived demand for three of these minerals, which are cobalt, copper, and nickel. And we will use Google search data. And so, in order to develop these proxies, we need to rely on two ideas. The first one being that of derived demand, which dates back to Lowinger and Ram and to Berleger, according to which basically the demand for a good is also coming from its demand as an intermediate good for production of final good. And so we use this interpretation to basically say that the demand for copper, cobalt, and nickel also comes from the technologies driving the energy and digital transition that uses these minerals, of course. And a quick disclaimer about this is that throughout the presentation, I will talk about transition, but what I will be precisely referring is the so-called twin transition, so both the energy and the digital one. The second notion that we need is that is the idea that basically online search volume captures consumer preparatory steps to spend, which is basically an idea that is useful to us to say, okay, if people looked for something on Google, they're probably going to buy it later. So by using these two notions, basically we will be able to give this derived demand interpretation to our proxies. Once we have our proxies, we will use them in structural VR model for the minerals market. And in particular, we disentangle four types of shock. The first is a classic supply shock, whereas we have three demand shocks. The first is related to aggregate demand. Then, only thanks to our proxy, we'll be able to disentangle what we call a transition demand shock, which is what we think is the main contribution of the paper. And finally, a metal-specific demand shock. And concluding, in the extension, we will use local projections to see if structural shocks of mineral markets have a spillover effect into the macroeconomy, and specifically if they will have inflationary effects on China, the EU, and or the EU-US. Okay, so let's start. Let's start from the construction of the indexes. As I said, we use Google Trends data, which are nothing but basically Google Trends is a platform provided by Google that shows how much a given keyword was searched in a given region and in a given time. It actually does not display the exact number of times, but rather an index proportional to these searches. And so in this image, you can see, for example, the series for three words that are battery, Tesla, or nickel. And so this is a bit the starting data. And what do we do with this data? Well, we basically follow a recent literature that uses Google Trend data to build demand proxies. And in particular, the two most important papers are Moller et al. And Warp and Schutte. And following them, what is the approach? Well, basically, at first, you need to gather a lot of Google Trend series that in our case were 108. And obviously, given our derived demand interpretation, this Google Trend series should be related to these technologies driving the transition. And so the four main categories that we identified are smart devices, electric vehicles, batteries, and solar panels. Once you have the data, the Google Trend series, you need to isolate to make them stationary. And in particular, in our case, we use the Hamilton filter for this purpose. And finally, the literature says that you should use targeted PCA, which is a technique introduced by BioNG, according to that is basically a PCA where you can give a sort of direction to the PCA in the sense that you can use Elastic Net to select the most relevant Google Trends to explain a series that you choose. And in our case, we used the Elastic Net to select the 10 most relevant Google Trend series for explaining the cyclical component of real price of our mineral M. And then once you have these 10 most relevant queries, you just simply do PCA just on those 10 that were selected through the Elastic Net. And what we end up with is this DDP, which stands for Derived Demand Proxy, which again is basically capturing the technology link demand of mineral M. As a validation exercises, we plot our DDPs against the respective price, and we can see here in this plot that in each case the correlation is high. If I recall correctly, is around 50% for cobalt and more than 70 for copper and nickel. Okay, so we have the proxies, and we basically estimate a structural bar for each mineral. Yes.
Very quick question. So do you need to take into account the noise? Is it noisy, this type of data? And do you need to deal with the estimation effect that comes from this? Or
Yeah, well, basically, we use the Hamilton filter exactly to isolate the trend and reduce the noise, basically. So yeah, but otherwise, if you use the whole technique on the raw series, yeah, it's a bit of a mess because they
you have
tend to have
effects, right? I guess.
Sorry.
I guess you have some maybe effect coming from the proxy that can be noisy or something like that, right?
But do you mean in the structure of the R, sorry, or in the...
Yeah, I mean, when you take this data from, let's say, Google, and then of course you use it for the estimations. I'm just wondering whether, I'm just curious, I mean, just to see whether there is some noise that is coming from this data that can affect the estimation.
No, I mean, for how we estimated, no. But yeah, if you directly use Google Trend, could be definitely the case.
Okay, thank you.
Okay, so for each mineral that I recall are cobalt, copper, and nickel, we estimate a structural VAR of order 3, where the vector of observable YMT includes growth rate of world or production of the mineral, the growth rate of world industrial production, sourced by Baumeister and Hamilton, 2019, and then we have the log of real price of the mineral, of course, and finally we have our derived demand proxy. The sample is from the end of 2006 to the end of 2023, and the estimation is done with in the spirit of Arias et al. 2018. However, the big question is, which shocks do we identify and how? Well, basically, we have 4 variables, so we identify 4 shocks. The first restriction that we use are 0 and sign restrictions that you see in this table. And I don't have time to explain all of the signs, but basically, if you exclude the transition demand and the DDP, the transition demand column and the DDP row, you have standard signs. You can look at the oil market literature for that, like Baumeister and Hamilton, Killian, etc., for reference to the oil market. But also there are recently coming up new papers about critical raw materials, like there is one by Boyer et al. And so, excluding this column, which is of course our novelty, we don't know. We do everything standard. However, what we care about more is the transition demand. And how do we find a transition demand shock? Well, for us, a transition demand, one thing I didn't mention is that here all the shocks are normalized to have an increase in price. So what we're seeing here is basically a negative supply shock and positive demand shocks. And so how do we find a positive transition demand? Well, first of all, it's a demand shock, so it should increase prices. And most importantly, it should increase our derived demand proxy, because this transition demand should occur in this model through the channel of derived demand for the technologies, basically. Whereas for the metal demand, that is a shock that is a sort of a residual demand shock for the metal, we imply the classic shocks, the classic demand the metal demand shock signs. However, we put a zero on DDP, which is exactly what enables us to distinguish our transition demand, basically. However, maybe some of you have noticed something that is not correct in this table. That is that potentially the aggregate demand and the transition demand are confounding, because if you think about it, if you get all pluses here and a plus here, then these two columns will be equal. And for this reason, we need another restriction, which is a magnitude restriction, that basically tells us that world industrial production should respond more to aggregate demand than to transition demand. And that is not only an impact, but also on the subsequent free periods. And this is enough for us to have a perfect distinguish between these two shocks. Okay, let's look at the results, and we start with the structural impulse responses, where in each end of real prices, and in each column you have basically a mineral. And what can we see here? Well, first of all, a couple of technicalities about these impulse responses are that we are looking at one standard deviation structural shocks, and that the inference is done through the Ainoue and Killian methodology. Okay, so what can we understand from these impulse responses? Well, first of all, in all cases, basically aggregate demand shock has the biggest impacts on prices. On the other hand, the mineral demand shocks seems to be the less relevant, because they almost never have a significant effect, basically. Whereas supply shock are very important for cobalt and less for copper, and even less for nickel. However, what we care most about is the transition demand. And what we see, okay, for cobalt, we see nothing, basically, no interesting effect. However, for copper, and especially for nickel, we find something interesting. That is, unlike other shocks, the transition demand eats the price. It doesn't basically it doesn't eat much the price on impact. But we can see how the response builds up over time. And so the transition demand shock is characterized by impulse responses of prices that are higher in not on impact, but in subsequent period. And this is something that we found. 5? Yeah. What we find interesting is because if you think about transitions are not a structural, an immediate change, are more like gradual shocks, and so this is relevant to notice for us. Then in a second exercise, we compute forecast error variance decomposition, and specifically we do it over 2 different subsamples, and because we wanted to see if the role of transition demand is more relevant when considering a more recent subsample, which is what we expect because the transition was something that for sure was most important between 2015 and 2023 rather than from 2006 to 2015. So we split the sample. To be fair, it's half. It's an half split. And what do we notice? Okay, first of all, before even considering the sample, in all the possible forecast error variance decomposition of the real price, what we see is that the contribution of the transition demand, which is the orange bar, increases. Again, showing this fact that this transition is more relevant to consider when we want to look at longer horizons. Whereas looking at the splits at the subsamples, so we can see that for cobalt, our expectations are completely met, as the transition demand goes from 25 to percentages like 60. For copper. Whereas for cobalt, this is not the case, and for nickel, the result is similar. However, if we want to look at what happened during specific historical events, what we need to use is historical decomposition. And so in this case, we took two episodes of increasing prices. The first one being in 2009, which was due to mainly the rebound from the great financial crisis. So we expect this to be driven more by aggregate demand shocks, which is what we see indeed. Whereas on the second panel, and on the right panels, what we see is the period between July 2021 and June 2022, which was a very particular period for critical raw materials because a lot of stuff were happening. First of all, we were recovering from COVID. So again, aggregate demand shock should play a role, and they do in these plots. Then there were supply shortages because of COVID again, and so also supply shocks should have played a role, and they do again. However, another interesting and very important thing was that at that time the demand for critical raw materials was increasing. For why? And for this was for the surge in demand for electric vehicles, which is the perfect example. The perfect example of what we call a transition demand shock. And indeed, on the right-hand side, we can see how the orange bars are more present than the left-hand one. And most importantly, they are always positive, whereas often on the left, they are also negative. So concluding very, very briefly, our final exercise want to look at the following thing. Okay, basically we saw how real prices of minerals react to different shocks. However, these minerals, the price of minerals varying can have impact on consumer price indexes. And so we estimate this local projection, where on the left-hand side, we have a headline CPI for China, the EU, or the US, one at a time. And on the right-hand side, we insert all the shocks that we have from our structural BAR for each mineral and for each type, one at a time. And as controls, we include the lags of CPI growth, the lags of world industrial productions, and the prices of the other two minerals, all the minerals but the one considered. And for time reason, I will only show results about China CPI. And what do we see? Well, I think that what we do see is echoing in some sense what we saw with the prices inputs responses, because there we saw that MD shocks have no effect on prices or negligible effects. And so this is shown by this impulse response in the sense that of course, if they don't affect prices so much, they cannot influence consumer prices so much. Similar for supply shocks, whereas especially at looking at longer horizons again, we found that aggregate demand have persistent effects, but also transition demand, indicating once again from this, let's say, increasing shape that the effects of TD are not coming always on impact, but rather they require some lag and then they have some persistence, let's say. Okay, so that was it. Basically, the key findings of this paper are that TD shocks, transition demand shocks, generate persistent price effects. However, the AD shocks remain the main driver of mineral prices. And finally, with the last exercise, we saw how these translate into CPI responses. And I conclude with a note that is that all of this work does not consider AIs. And so it is possible that our transition demand estimates are even a sort of lower bound because, of course, AI is a new source of demand of the very last few years that increased a lot the demand for critical raw materials, but it will be probably the job of the next paper, perhaps, but not of this one to quantify this.
Great,
Uh,
thank you very much, Marco. So let me stop the recording, and I think we are